For Lab 5, I decided to take physics in my own hands and use the principle learned in class to examine physics in something I was keenly interested in. So I decided to use something related to my music and guitars to help me out. What I'm going to do is analyze the movement and sound of these guitar strings to prove the energy principle. That's the shortened version of the story. To calculate this, I'm going to need many things. Total energy is kinetic plus potential and a few other energies including vibrational, thermal, and other energy that turns into sound. Analyzing the sound files, I will find the frequency of the wave and use that to find the wavelength, use that to find the velocity of the wave traveling through the string, which I can use 1/2 mv squared along with the string mass to calculate kinetic energy. Then, using data about the guitar string, including the string tension constant and the amount the string is displaced, I can calculate the spring potential energy. It ends up that there is a bit of energy left over, the internal, thermal, and sound energies, but we can say that the energy principle holds true for this example too. I used a lot of formulas and code to figure out this problem, but it all started with the sound file. We know that lambda, or the wavelength, is the inverse of frequency, and that frequency is the inverse of wavelength. We also know that the velocity of the wave on the string is the square root of the tension over mass per unit length of the string. Mass per unit length is the string mass over the string length. Using data from the string and guitar manufacturer, we can find this data. Our string potential energy will be the integral of fx dx, which becomes 1/2 fx squared. To get the original values for frequency and wavelength, I inputted a sound file for an individual string to get its wavelength. This code, originally written by my TA Gable Wadsworth, but pinpoint edited for my specific cause by me, will find values at the top of the wave and then find the amount of seconds in between them and then take an average. This will give us how many seconds are in between each crest of the wave. Then, the inverse of this number is the wavelength we are looking for. Running this code for the high E string gives us a value of 333.33. The actual wavelength for the high E string is 329.6, so we're not too far off. And it was likely because my guitar was out of tune anyway, not because of the imperfections in the code. I used this formula to get the rest of the frequencies of the guitar, changing the file name and some other minor data per string. After getting the values for the frequencies of the guitar strings, I watched my video for the motion to use that will give me the potential and kinetic energy. With a frame rate of 30 frames per second, only the thickest two strings were trackable, so I ended up using only the low E string to use as the example for motion. Here we will track a single point on the video as it moves over time. I use the center point of the E string's pole piece on the neck pickup. I use this for several reasons. First, because it maximized the contrast between the strings and the background. And it was close to the middle of the string, so it vibrated a lot compared to at the bridge or nut at the top of the neck. I had to change the axis and the calibration stick every frame to keep the numbers consistent. And as the graph to the right of the screen shows, and the data, it worked out pretty well. Now that we have this motion tracked, I will export it to a CSV file and then use it to track motion in the Python code. To start out the code for the energy principle, I used a combination of things I'd learned from the black hole lab and spring energy lab. To start out, I used the basis of the black hole lab and created a point on my guitar string to watch. I specified the mass of the string by the manufacturer's specifications. Then I read the CSV data file of the points I had found from the tracker. I computed the velocities to be later used in the code. For the calculation loop, I calculated the velocities to be used in the kinetic energy, and then the spring constant solved for earlier, and x in the spring potential is the difference between the spring's position and its position at rest. Then I graphed the kinetic energy, potential energy, and then a combination of the two, while accounting for the 1 to 5% of energy that leaves as other energies. Through research, I found that only about 5% of the energy is transmitted into sound. The other 95 lie in kinetic, vibrational, heat, and friction energy. Let's watch the code in action. A few notes. As seen earlier in the code, I start time at 0.33 seconds, because before then I hadn't strummed the guitar, so there was energy added to the system at this time, when I'm trying to prove the energy principle. The energies are in order of blue, kinetic, red, potential, and green for total energy of the system. The lines seem to be very staggered because it's moving very fast compared to the other spring lab. And the screen above, we watch the fixed point move according to the origin. We see that total energy stays near zero, as predicted, but with that 1 to 5% of energy that is not accounted for, including sound energy. To conclude, the energy principle holds true. Energy is neither created nor destroyed. Guitars do not have magical energy powers. Thank you.